Okay. So that's the meaning of random continuous. Okay. Okay, let's move forward. Yeah, this is just a introduction. I mean, remembering what we already talked about. For example, what is the discrete random variable? What is the probability distribution? Yes, actually, this is for y-axis. Yes. How do you construct the probability distribution for discrete random variable? I hope you already know this one. And what is the density curve? Yes. Uniform distribution. Maybe the uniform distribution, the thing that maybe you have to know, something like this. Uniform. Uniform means that in certain random variable, in certain range of random variable, let's say A and B, this is the variable X. Because of uniform, uniform means equal probability between A and B, there is a same probability. Let's say the B minus A equal to 2. So what is the value here? Anyone can guess? Zero point 0.5. Why 0.5? Because uh, uh, the size under the curve it should be 1. Because of the size should be 1. If we know there is a 2 here, so we should multiply by 0.5. So 2 by multiply by 0.5 equal to 1. Okay. This is the uniform distribution. And what is the continuous random variable, and how do you define a probability distribution for a continuous random variable? That's what we're going to talk today. Actually, this is the definition of a random variable. Yeah. Actually, you already know. Okay. You have this graph here. Yeah, this is y-axis is random variable, and x-axis is random variable x, and y-axis is a probability. And this one is probability function. Yes. I want to ask you, what is kind of distribution function depicted by this graph? Whether discrete or continuous? Please answer my question in chat box. You can write whether discrete or continuous and why. Why you call it a discrete, why you call it as a continuous. Please write the answer on the chat box. Only 2 participants? How about the others? Narendra, what is your answer? No answer, Narendra? Connection problem. Okay. Nadia Miesha. Okay. Maybe Narendra, Daniel say that he might has a connection problem. Okay, so discrete, Narendra discrete. Nadia, Nadia. Yeah, why? Still Nadia, why you answer discrete or you say it is discrete? Countable, finite. It is countable. Okay, anyway, thank you very much for your participations, for answering my question. But actually, the correct answer, this graph can be classified as continuous. Continuous in what? Continuous in this period. Continuous in this period. You can see here this graph. In the left side or in the right side, there is no other component. There is no other random variable axis. There is no here, this no here, and the x being maybe 0.2 here, the probability is 0. Also, greater than 0.7, also 0, 0, 0, 0, 0, until infinite minus infinity, or here positive infinity. And the probability only exists in this range between 0.3 until 0.7. And this area, it should be 1. The size of the area should be 1. So you can guess here, what is the value here? We can simply compute that 1 by 0.4 or equal to the 10 by 4. This is here. To fulfill this size being 1. Okay. Any questions?
No, sir.
No. Okay. So let X be amount of time in minutes that a particular San Francisco commuter must wait for a BIRT train. Suppose that the density curve is uniform distributions. Draw the density curve for 0 until 20 minutes. What is the probability that the wait is between 12 until 20 minutes? So we draw here the uniform distributions. Oh, sorry, it should be from 0 until 20. Okay. So what is the value here? The value is 1/20, right?
Yeah, 1/20.
Okay, should be 0.05, right? Okay, 0.5. Okay. So what is the probability that the weight is between 12 until 20? So let's say here is 10. Oh, here is 10 and 12 is here. Okay, so we have to compute the area that I'm make a pattern here. It's like a cross fish. Okay, yeah, here. What is the size of this? Size of this? Actually, we can simply compute that the size of this area is 8. Why come from 8? Because 20 subtract by 12, 8 multiplied by 0.05. So it is equal to 0.4, right? What is the probability the white is between 12 until 20 is 0.4 or equivalent to the 40%. So it's mean that we have a 40% chance for having the train between 12 under 20 minutes. So this is the curve and this is the result here. 0.4 or 40%. Maybe for the mathematical expression here, maybe you should notice here that the probability between 12 until 20, mathematically we can express being like this: 12 greater than X, probability between 12 and 20. Yes. This is the random variable that falls, and this is the range between 12 and 20. Mathematically, we can write things like this. Okay. And same with the discrete random variable. The random variable in continuous also can be characterized by the mean, mean and variance or standard deviations. Standard deviation without power 2, only power 1. Yeah, so actually this is the two parameters that characterize the random variable. Okay. Okay. Based on the pattern of the how the curve shape like maybe bell shape or like rectangular. Until now, we already understand about the uniform distribution, that the graph is being like this. This is the uniform for probability for a given number. How about the normal? The normal also we have a pattern being like this. The shape is being like this. This is a symmetric between the left side and right side. Same size and characterized by the mean and the variance. Okay. This is just example. Nah, this is the normal distribution. This is the normal distribution characterized by mu and standard deviation or variance. If we write being only sigma like this is the standard deviation. But if we write being like this is a variance. Okay, from this figure we can identify. You can see this is the graph is like a bell shape, like become sharper at the top, and the slope for the left side and right side here decreasing. And this slope is from minus infinity and until positive infinity, close to the zero, yeah, close to the zero, but not or never touch the zero, just limit. And for the peak also represent the center of is like a mirroring. In this point, we can say this is the mean. This is the mean for the top point here. Actually, the mean is here because the mean is a member of random variable. But the y-axis here is a probability. You can see here, or you can remember that in discrete random variable, this graph is a PMF, right? PMF, probability mass function. But for continuous, we say as PDF, probability density function, density functions. Okay. How about the standard deviation or variance by seeing this graph? From this graph, actually we cannot determine. Actually, we cannot determine by IS. We cannot determine for the mean or average. We can here we can determine for from the graph. But for the variance or standard deviation, we cannot. Okay. Okay, this is how we can compute, but actually we skip this one. Okay, we jump to this more specific discussion about the normal distributions. If any question, please write on the chat box. One thing, not one thing, but several things that we can derive from the normal distributions. First, mean, median, and mode are equal. This is the mean, this is the mode, this is also the median. Okay, and bell shape and is symmetric about the mean. Yes. This graph, the red dashed line here, this is like a mirror. Mirroring between the left side and the right side. Because a mirror, this is really symmetric. The size of left side also equal to the right side here. The total area lies under the curve is 1. Yeah, area here is equal to 1. There is no, should be perfect 1, no less or greater than 1. We can say also 100%. In this slide, we want to characterize not only from the mean, but if we know or there is a given standard deviations, where is the point of standard deviation actually from this graph? You should not hear that the standard deviation should be given. And then after that, we can determine where is the locations. For example, the standard deviation is sigma here. The sigma, by definition or by formula, the position is here. This point is equal to mu plus standard deviation. Otherwise, for the left side is mu minus standard deviation. So the white here is equal standard deviations. Yeah, white here is equal to 1 standard deviations. And this point more wider, yeah. This point, it is equal to mu plus twice standard deviation. Also for this point is mu minus twice standard deviation. Okay. Also here, this point also minus mu plus 3 standard deviation. This point is mu plus minus yeah, no plus 3 standard deviation. Okay. What is the implication from dividing based on the standard deviation? Actually, we arrive this graph. You can see the area under the curve we can classify as purple, and this is red, and this is green. Yes. Purple area, red area, and green area. Actually, this is start with minus infinity and the end of positive infinity. Okay. Okay, you can see here. You can see here. This is minus standard deviation. This is plus sigma plus standard deviation. Area in this purple here limited by minus standard deviation until positive standard deviation. The size is 68%. 68% for the purple. Yeah. And if we add, we start more wider from the twice standard deviation, from minus twice and until positive the twice standard deviation, we arrive at that 95% under the curve. And if we arrive or we complete with the green area, we arrive at the 99.7%. Okay, that's the empirical rule or characteristic of normal distributions. Any questions?
No question.
No question. Okay. Okay, let's move forward. We have a exercise here. Let's say the mean of population is being 4.2 hours and the standard deviation being 0.3. Actually, what is the problem? We have a problem here. An instruction manual claims that the assembly time for a product is normally distributed with a mean of 4.2 hours and the standard deviation being 0.3 hours. Determine the interval in which 95% of the assembly times falls. 95 you characterize from this behavior, from this characteristic. You can see start from this point, twice standard deviation until twice standard deviation here. Okay, so we can easily compute that the starting point is mean minus twice standard deviation, and the mean is 4.2. The subtract by 2 multiplied by 0.3 is equal to 4.2 minus 0.6, so 3.6. That's the answer here. Also for same ways, but this is positive standard deviation, 4.2 plus 2.3, 0.2 plus 0.6 is 4.8. Okay, we arrive at this point. Okay, so 95% of assembly time will be between from 3.6 hour until 4.8 hour. Okay. Any question?
No, sir.
No. Okay. Maybe my question is, what is the size of left green here only? What is the size of left green only? Left green area only. What is the size? How many percent? You can exercise by yourself. I'm waiting. Maybe for 5 minutes. Yeah, Daniel Siboro writing is about 2%, but please write the exact number. Exact number. It can be computed. Yeah, it can be computed exactly. The answer is exact. %2.5%. Let's compute. Let's compute. Yeah. You can see here from the red area and the purple. Red area, both red area, this one and plus this one is 95, right? 95%. So the rest of the area is 5%, right? So, 5%. 5% for the both green, right? For both green. So divided by 2 for on left green only. So is equal to 2.5. Okay. We can say from this result, probability, there is 2.5 probability that the assembly time maximum 3.6 hours. Okay. Also, another way to compute 2.5% actually from integrations. So the new information from this graph, yeah, the normal distribution this has this PDF. Sorry, there is an advertisement. Okay, so the PDF of normal distribution is graphically we can see being like this, but not bad. Moreover, this function or this graph has a function. Mathematically, we can express being like this. The PDF equal to the 1 by standard deviation square 2 pi exponential power minus, this is the x, minus by mu power by 2 divided by 2 variance. Yeah. That's the function of this graph. This function depends on the value of the variance here and the value of mean. So, computing the green area, left green area, it is equal to the integration from the minus infinity to the, what is the limit here? 3.6 dx. Why dx? Because this is in x. Actually, this one should be same. Okay. If you don't believe, you can try by yourself integrating this formula. And the result should be 2.5%. If not, maybe not correct. Not maybe. If not, it is not correct. Okay. Any questions?
No, sir.
No. So I'm asking here, what is the probability? I'm writing here. I'm writing in chat book. What is probability for assembly time, maximum assembly time being 3.5 hours? Yes, you have 15 minutes to compute these questions. Okay, we will finish at 2 p.m. Okay, thank you, Goldie, for computing. Actually, so the first method we can write based on the integrations, which is the integration is from minus infinity until 3.5, right? 3.5. for the distribution function is 1, 2, pi here, 0.3 exponential minus x minus 4.2 power by 2 divided by 2, 0.3 power by 2. Okay. You can compute from these integrations. This is dx. Another way, we can compute using the internet. I will tell you how to compute using the internet. Okay. Everybody see?
Yes, sir.
Okay.
Yes, sir.
Notation here. Okay. You can see here, this is the, actually you can access for many websites to compute this probability. Yeah. For any website. For example, this is I use Keisan Casio, but it's really not advertisement. But this is only random pickup from the website. Okay. You can see here, this is the graph that represent actually same with the graphic in the slide. I will make zoom maybe. Yeah, zoom greater. Okay, it's good. Okay, you can see here the mean is 4.2. Actually, how to write here? Actually, we can draw here. Mean just write 4.2. Okay, and then the x here is depend on the problem, because we want to know the probability that the maximum assembly time is 3.5. Means that you can see from maybe this figure, this is 3.5 right here, the maximum. So this area from this infinity, that's why this draw being red line here. This is this point is equal to 3.5 here, 3.5, and also we put the number of standard deviations become 0.3, and then we can calculate. We can compute. Just execute this one. Okay. Yeah. The graph is being like this. Actually, this graph, the graph under the red line, what is the result? We have a 3 result here. What is the value that we want to know? Actually, this one. Why this is not this one? Actually, this one, probability density, represent the value at the point here. This one. This value represent the area below the red one, the red line. And this value represent the area, the rest, the blue area here. So you can see here it is equal to 0.0098. If compute to the percent is equal to 0.98%. And the rest is 99.9 no 99.00 what 0 maybe 2, yeah, is equal to 2, yeah, we can round it by 2, yeah, this is percent. So you can see here the area for below the red line is only 0.98%, and the rest of this area is being 99.02%. That's the result. Actually, also we can check from this one. This is the probability density. This is how we can compute. And the lower cumulative, it is exactly same what we already expression of integration here. You can see here integration of minus infinity to the x. X here is represented by 3.5, right? This is the probability density function here, actually same with this one. The mean is 4.2 and the standard deviation is 0.3. Okay, and the cumulative is the rest. I mean, integration from the x 3.5 until positive infinity with the same function here. Okay, I hope it is clear. Any questions? Okay, Daniel, we have a question here. We calculate that the percentage 3.6 and below is 9.5%, but here it say that 2.275% instead. Okay, let's check together by this one. Okay, 6, 2, and execute. 0.0227.5. Okay, let's check. The green one, right? The green one is for this 95. 95%. So the rest is 5%. Okay. The 5% by 2.5. Standard deviation, it's correct. Okay. Okay. Tiga 3,9. Point. Yeah, it is a good question. Actually, how to say? 2.5 here. Let's 2.5 here is just an approximations, but how to say? Yeah. If we have a, for example, the mean is being 0 and the standard deviation is 1, and then the percentile is -2, right? -2 it should be, yeah. Yeah, actually, how to say? 90 divided by 2.2. Yeah. Actually, this Which one? This one. This one is an approximation. The exact result is based on the computation. Yeah. So yeah, also it is not true that 2.5 is equal to 2.225. Yeah, but you can approximate that this area is 95, but maybe based on the real computation is not really exact with 95. It's around 95, something like that. Because the integration of this is, you can see here from the real computation, there is still a number after the zero. You can see there is a still number after the zero. This is actually depend on the significance. If you consider a wider number here, it means that you are really accurate. But if you consider only several number here, only small number, means that you can make an approximations, something like that. Okay, that's my answer. So from this point is approximations. Yeah. For twice standard deviation, this is can be approximately around 95%. And for this one is around 97% for this one. Something like that. Hopefully it is answer your question. But for the real computation of the real result, first you can make from this integrations, or the second you can check by the software or computation applications, something like that. Okay. And the third ways, or the third method, is using standard normal. Standard normal is, what is the standard normal? Standard normal if the mean equal to 0 and the standard deviation equal to be 1. This is the standard normal. You can see here the standard normal, the graph is being like this. The mean is 0, and you can see here for the random variable always from minus infinity to the positive infinity. And the left side, if we have a mirror line here, the left side always occupied by negative random variable, and for the right side always positive. So this is the standard normal, and from this graph we have a table standard standard normal probabilities. Okay. Clear. Wait, I'm clearing. Okay. Okay. You can see that the standard normal is always being like this. I point out again that the left side always negative random variable and the right hand side is positive random variable. So back to this point, 3.5 is located at the left side mean, right? Left side mean. So it should be around here, equivalently around here, 3.5. So how to compute the Z variable here? Actually, the Z variable is the X minus mu divided by standard deviations according to this formula. So we can compute here, let's say 3.5 minus 4.2 divided by 0.3. It is equal to, I write here, minus 0.6, right? 0.6 divided by 0.3. It's mean that minus 2, right? Minus 2. So the Z is minus 2. So we keep it this result and check the table. Okay, we have table being like that, being like this. I explained to you about this table. This is the standard normal distribution table, and this is the standard normal, means that the with average or mean being 0, mean equal to 0, and the x-axis is the variable z here, variable z here, and this is the graph, and the orange one, this is the area that we want to compute. Okay, and you can see here there is many columns. Actually, for the most left column here represent the random variable z. So this is for from -3 until increasing, -2, -1, and always increasing, means that from this point to this point here. And this one here, another column here, represent the comma, comma after, for example, this one represent, for example, we know that the z that we want to know is z is -2, right? -2.00, right? minus 2 is 0.00. So we search from minus 2, this one minus 2.00. Oh, okay. We look at this column and we arrive at this one. So the area in this orange is equal to 0.0228. So result from this is this one. Actually, this one is should be same with where is this one. This one, right? 0.022 and round it up, and we arrive at 0.0228. It's same with what we found on the table or from the table. Okay. Until now, we can compute using 3 methods, okay? Using integrations, using calculation based on the software or applications, and the third is based on the table, lookup table. Okay. Okay, any questions? No, sir. This is the how we can compute the Z variable. This is the parameter X that we want to compute, and this is the mean of our population. This is the standard deviation of our populations. Okay. Okay, this is another example. The test score for civil service exam are normally distributed with mean being 152, with standard deviation being 7. Find the Z score for person with score 161, 148, 152. Okay, yeah, we can easily compute using this one. This is the score from here. This is the mean. This is the standard deviation. And we found that for Z score is 1.29. 1.929. If we have X being 148, and this is the this is the mean here, and this, and we arrive at this point, Z. So this point at the right side, do you remember? This is Z. At the right side here, because of positive, this is negative, located in the left side. And for example, somebody has 152, so it's equal to the mean of the population. It's located here. So that's why the Z score is 0 here. Something like that. Okay. Any questions? We move forward to this one. Okay. Okay. Okay, this is the cumulative area. Cumulative represent the probability. For example, the probability of maximum 0 means that the probability x 0, it is equal to the integral of minus infinity until 0. This is PDF of z. dz, something like this. This is the cumulative. This is the cumulative fx. Okay, fx. You remember that cumulative distribution function at the discrete if x, something like this, probability that x greater than x. And this is x, yeah. Okay, something like that. So same ways, the cumulative in the continuous random variable, also the probability of x less than x. It is equal to integral minus, I write here, integral minus infinity to the sum x. This is PDF of x. Something like that. Okay, any questions? This is, for example, we compute or we want to know the cumulative for z score here is minus 1.25. Minus 1.25. This is the area. The black area here is around here, minus 0.25. And by integration, the result will be 0.1056. Let's check from the table. We still have a table. So the Z score. Z score is, you remember, minus 1.25, right? And based on the PPT, the probability Z greater than less than minus 25 is equal to 0.1056, right? Let's check. Minus 1, minus 1, 2. Okay, this one. 1, 2, and 5. 5, this one. Okay, let's check. Okay, this one. So this is just equal to this one. Okay. Equal to this one, yeah, the kotak. Okay. Any questions? No. Okay. Let's get back to the this one. Okay. Maybe the thing that you have to point out is this expression. This is the random variable that represent the x-axis, and this is the value that we want to know for the limit of the probability, and this is also the the sign. Actually, this sign is different with this sign. This sign, you have to include this one. But for these signs, you don't have to include, you must not include this one. If we want to know the probability Z, maybe less than 145, and this is not equal to the probability Z. (45). This is not equal. For finding this one, we can use a table. Actually, same what we already talked about this method. This is actually probability. This is the probability x 5, something like that. But for finding this one, you have to check this one. You have to be detailed this one. This means that this is not include this one. So it is equal to the probability Z. Maybe it's not clear here. Probability Z greater than 1.5. 1.5. This is, but this is minus plus 1. This is minus or equal to 1 minus probability Z greater than 1.5. Okay. This one. Minus, yeah, minus this one. Yeah. You have to be careful to see these notations. Okay. So if you want to know the integrations, for example, this one, if we write on the mathematical integration is like this. Probability. So integration between minus and minus. This is the PDF of x dx. uh, plus integration between one positive positive infinity df x dx. This one, something like this, sum up, and this is minus 1 minus integral this one plus integral this one. This is equal to this one. So from the table, from the equation, from the equation, how do we define this one? This one is let's check using the screen here. Okay. So we want to compute that one. So this is integral 1.25, right? Minus 125 x cubed. We have this one. We write on the note. Zero point 105. Yeah, let's say 1056. Okay, we point out here, and for integration, x. standard normal distributions. So is 1.17. Execute. So we want to know the this one 0.01. Okay. So we pick up this point. So we back to this one. After computations, this one is 0.1057 plus 0.921. If the total is equal to the 0.1060 plus 0.7 is equal to 0.226. Yeah, and this is still one minus minus. Okay, minus 1 minus this one is equal to 0.7734, something like that. So this equal to this result. Okay. Is it complicated? Okay. Daniel Sipuro can understand. Okay, good. How about the others? Can you understand? And which part that you did not understand? Maybe until now, I want to point out something important, yeah. The probability, let's say X less than 1, let's say this is 1 is just an example. It is not equal to the probability X less than 1. You can see here. And based on the graph, if we have a 1 here, this one it should be include, means that maybe we make a black, means that this line is include. But for this one, the one here, it doesn't include. So I don't make a black one. So the area is only this, but the one is not included. That's why this expression is not same, not equal. Usually in the table, to find the z-score, you have to check that the table is usually finding this area is based on this formula, meaning that probability x less than 1. This is 1. Usually in the table using this expression. And then how to find this one? Yeah, actually this one is probability is equal to 1 the subtract by probability x greater than or equal 1. Yeah, it is equal to this one. Please be careful. Be careful for this expression. Actually, this is not the same. Okay, any questions? This is summary. Yeah, summary is just summary. To find the probabilities with z less than that given value, read in the corresponding cumulative, this one. Find the probability is greater than the given value, subtract the cumulative table from 1. So if you want to find this one, given table this one, so it's just 1 subtract by the black area here. If you find the probability z is between 2 given value, means that there are many applications also we can compute directly, but if you base on the table, you can find from this one and then subtract this one if you want to find the black one. Again, if you want to find the black one here, so first you have to find the probability this one and then subtract by the probability of this one. So the rest of the black is subtraction between two probability. Yes. Any questions? Yeah, if no questions, we finish our discussion today. And I hope you clearly understand. If not, I already make recording.